The Evolutionary Powerhouse. Mastering genetic algorithms for optimization challenges in an era where complex optimization problems dominate industries from logistics to machine learning. Genetic algorithms stand as a revolutionary solution inspired by natural selection. These computational models mimic biological evolution processes to find near-optimal solutions efficiently. Unlike traditional methods that often get trapped in local optima, genetic algorithms explore vast search spaces through mechanisms such as crossover, mutation, and selection. This makes them particularly effective for nonlinear, multidimensional problem domains. Origins and core principles. Genetic algorithms trace their roots back to the 1960s when computer scientist John Holland began exploring how evolutionary principles could be applied to problem solving. His work laid the foundation for what would become a powerful metaheuristic technique. Holland's concept was simple yet profound. Populations of candidate solutions evolve over generations through selective breeding and random mutations. This process mirrors nature's ability to optimize traits across species over time. Natural selection analogy. Just as organisms with advantageous traits survive better, GA selects individuals with higher fitness scores for reproduction. Population-based search. Instead of single-point searches, GAs maintain diverse populations that explore multiple potential solutions simultaneously. How genetic algorithms work. A typical genetic algorithm implementation follows 5 key phases: initialization, evaluation, selection, crossover, and mutation. Each phase plays a critical role in guiding the population towards optimal solutions. During initialization, a set of random candidate solutions is generated. These form the initial population, which will undergo iterative improvements through subsequent generations. The evaluation phase assesses each individual's fitness based on predefined objectives. Fitness functions vary depending on the specific application domain, but always measure solution quality quantitatively. Selection then determines which individuals will reproduce. Techniques like roulette wheel selection and tournament selection ensure fitter individuals have higher chances of passing their genes. Crossover combines genetic material from 2 parents to create offspring. Single-point and uniform crossover are common techniques used to generate new combinations of features. Mutation introduces small random changes to prevent premature convergence and maintain diversity within the population. The mutation rate controls how frequently these changes occur. Components of a genetic algorithm. The effectiveness of any genetic algorithm depends heavily on its core components working together harmoniously. Understanding these elements provides insight into designing successful implementations. Representation. Solutions must be encoded appropriately for manipulation during recombination operations. Binary strings, real numbers, permutations, and tree structures are common representation formats. Fitness function. This crucial component evaluates solution quality objectively. It transforms raw data into numerical values representing how well each candidate solves the given problem. Selection mechanism. Various strategies exist to choose parent candidates for reproduction. Roulette wheel selection gives proportionally greater chances to high-fitness individuals, while tournament selection compares subsets randomly. Crossover operators. Different operators enable varied exploration patterns. Single-point crossover swaps segments between parents, whereas uniform crossover randomly selects features from both parents. Mutation operators. These introduce controlled randomness to avoid getting stuck in suboptimal regions. Bit flip mutation works for binary representations, while Gaussian mutation applies to continuous variables. Applications across industries. Genetic algorithms have found widespread applications due to their versatility in solving complex optimization problems. Their ability to handle nonlinear relationships makes them ideal for many real-world scenarios. In manufacturing, they help optimize production schedules, minimizing idle times while maximizing resource utilization. Airlines use them for route optimization, reducing fuel consumption and improving passenger satisfaction. The healthcare industry benefits from GA-based approaches in drug discovery and personalized treatment plans. Researchers employ them to identify promising molecular compounds with desired properties. Financial institutions apply these algorithms for portfolio management, optimizing risk-reward ratios. They also assist in fraud detection systems, identifying unusual transaction patterns effectively. In engineering design, genetic algorithms aid structural optimization, ensuring safety standards while keeping costs low. Automotive companies use them for crash test simulations and aerodynamic shape optimizations. Strengths and limitations. While genetic algorithms offer significant advantages, understanding their limitations helps developers make informed decisions about when and how to implement them. Advantages: GAs excel at handling large search spaces with numerous local optima. They can solve problems without requiring derivative information, making them suitable for discontinuous functions. Disadvantages: convergence speed varies greatly depending on parameter settings. Poorly chosen parameters may lead to inefficient performance or failure to converge entirely. Parameter tuning remains a challenge as mutation rates, population sizes, and selection pressures significantly impact results. Too little variation leads to stagnation. Too much causes instability. Interpretability issues arise since evolved solutions sometimes lack clear human understandable explanations compared to other analytical methods. Debugging can become challenging when unexpected behaviors emerge. Design considerations for effective implementation. Creating an efficient genetic algorithm requires careful consideration of several factors that influence overall performance and reliability. Problem encoding. Choosing appropriate encoding schemes ensures compatibility with selected operators. Permutation encodings suit scheduling problems, while binary encodings work well for feature subset selections. Fitness landscape analysis. Understanding problem characteristics helps determine operator types and population size requirements. Multimodal landscapes benefit from larger populations, maintaining diversity. Elitism strategies. Preserving top-performing individuals prevents loss of good solutions during generation transitions. Simple elitist strategies save best individuals automatically before applying genetic operators. Termination conditions. Setting reasonable stopping criteria avoids unnecessary computation time. Common conditions include reaching a fixed number of generations or achieving target fitness levels. Hybrid approaches. Combining GAs with other optimization techniques enhances capabilities. Integrating local search methods improves exploitation power after global exploration phases. Evolving beyond basics. Advanced topics. Modern research has expanded beyond basic GA frameworks, incorporating advanced concepts to address emerging challenges in optimization theory. Multi-objective optimization. Traditional GAs focus on single objective functions. Recent developments allow simultaneous optimization of conflicting goals using Pareto front analysis and NSGA2 algorithms. Parallel processing. Implementing parallel computing architectures accelerates evaluations by distributing workload across multiple processors or machines. GPU acceleration shows particular promise for large-scale problems. Self-adaptive parameters. Intelligent GA variants adjust control parameters dynamically rather than relying on static settings. This enables automatic fine-tuning of mutation rates and population sizes. Constraint handling. Specialized constraint handling techniques ensure feasible solutions remain viable throughout evolution. Penalty. Function methods and dominance-based approaches show varying degrees of success. Future directions and research trends. Ongoing advancements continue pushing the boundaries of what genetic algorithms can achieve across different application areas. Integration with deep learning architectures promises exciting possibilities for hybrid intelligent systems capable of tackling previously unsolvable problems. Reinforcement learning combined with evolutionary strategies opens new avenues for autonomous system development. Quantum-inspired genetic algorithms leverage quantum computing principles, offering novel ways to represent and manipulate genetic information. Early experiments suggest improved efficiency in certain optimization tasks. Evolutionary robotics represents another frontier where GA-driven adaptation enables robots to learn locomotion skills autonomously through trial-and-error processes similar to biological organisms. Emerging fields like neuroevolution combine GA techniques with artificial neural networks, creating self-improving AI systems that evolve their own network structures and weights over time. Conclusion: genetic algorithms provide a robust framework for addressing complex optimization problems across various domains. By mimicking natural selection processes, they offer innovative solutions that traditional methods struggle to achieve. To harness their full potential, developers must understand fundamental principles while remaining aware of practical considerations influencing implementation outcomes. Continuous experimentation and adaptation ensure these evolutionary techniques remain relevant in rapidly evolving technological landscapes. HTML